Cardstock is an amazingly versatile and strong building material. Using a few simple techniques and tools for cutting, folding, and gluing cardstock, you can construct projects much simpler than this cardstock cuckoo that make it easier and fun for you to learn math and science. Let me show you a sample of AIMS activities that use cardstock. I'll start with some simple machines. This simple machine is called a wheel and axle. Turn the straw axle and the worm pops up. Looking at the back, there's a wheel with the axle placed off center. This is called a cam, with a cam follower that raises and lowers the worm, all made from cardstock and a plastic drinking straw. This lever demonstrates how 2 monkeys can lift 6 monkeys. The monkeys are identical jumbo-sized paper clips. Each paper clip weighs 1 gram. 2 grams lifts 6 grams. Check out the AIMS video that shows you step by step how to construct this project. Using a wheel and axle, the weight of 2 monkeys will again lift the weight of 6 monkeys. The wheels are cut from cardstock and the axle is a plastic drinking straw. You might think that gears are too complicated to be made from cardstock. Watch this. To make a gear, we start with a pattern on cardstock, fold the teeth, glue the teeth to a base pattern, glue the base to the end of a toilet tube, and we have a finished gear. Gears turn in opposite directions. Here, the driving gear turns clockwise, while the merry-go-round turns counterclockwise. Not all gears are wheels with teeth. The straight gear is called a rack, and the circular gear a pinion. The rack and pinion is commonly used in the steering mechanism of cars and trucks. Toy cars with low friction wheels are popular with upper elementary students and make for exciting force and motion activities. The cars used in these activities run on track made from cardstock. Pieces of straight track are easily folded from cardstock. Sections are glued or taped together to form straight tracks of any length. Even curved pieces are easily made by cutting and gluing a piece of cardstock. It's even easy to make a car launcher from cardstock, a rubber band, and a paper clip. With this launcher, a consistent force from weak to strong can be applied to the toy car. Speaking of forces, structures built from cardstock are a fun way to learn about the forces architects and engineers have to consider when building a large structure like a bridge. This is a cardstock model of a beam bridge. This simple beam won't support the weight of even a single car. But when formed into a U-beam, it will support the weight of more than one car. Adding T-beams glued to the bottom of the U-beam makes the bridge very, very strong. The triangle is a basic shape used to build strong structures. Look at the triangles in this model of a truss bridge. Each beam in the truss bridge is made from a triangular shaped pattern folded and glued along one side. Now, let's look at some examples of how cardstock can be used to make models for geometry. This is a geobar. There are patterns for long and short geobars. The long geobar is 8 inches and the short geobar is 4 inches in length. Both long and short geobars can be cut into shorter lengths and extra connectors are provided. Here, made from geobars, is an equilateral triangle, a scalene triangle, an isosceles triangle, and a right triangle. Four geobars glued together make a four-sided figure called a quadrilateral. Here's a rectangle and here's a square. The flexibility of the geobars dynamically illustrates that squares and rectangles are parallelograms. This quadrilateral has pairs of adjacent sides equal. It's called a deltoid or kite. This quadrilateral can be flexed to make a trapezoid with just one pair of parallel sides. Special geobars with built-in connectors make it easy to construct the edges of three-dimensional structures. This is the edges-only structure of a triangular-based pyramid, the tetrahedron. This is an edges-only structure of a triangular prism. And here's a square-based pyramid. This structure, made from 12 edges, can be flexed to form an edges-only model of a hexahedron, or as it's more commonly called, a cube. This geobar structure is flexible enough to show that the edges-only structure of a cube can be transformed into this structure. The flexibility of cardstock can be combined with the flexibility of a rubber band. This project demonstrates that the base angles of an isosceles triangle are equal. This one shows that the diagonals of a rhombus bisect each other at right angles. Would you like to learn the simple techniques used to construct each of these projects? If so, visit our website.